Today is the day we talk about security. Are you safe? No, wait. Don't answer that question. I don't care about that right now. The real question is whether your systems are safe, whether they're secure. No, wait. Scratch that as well. That's not today's topic. Here comes the real question. How can we secure everything without making everyone suffer? Yeah, that sounds about right. The following questions need to be answered when talking about security. 1. Is the access to your system secure? Is it done in a way that prevents unauthorized access to humans and processes? If that's the case, what can those who do have access do? Second, once you do have access to manage specific types of resources, what is required to ensure that you will follow good practices so that resources are created and managed following specific rules? 3. How do you know what you are running? What are all the components included in that something? Next, are you sure that what you're running has not been tampered by anyone or anything else? How do you know that there are no known vulnerabilities in what you're running? And finally, how do you store and retrieve confidential information? Those are the pillars of the questions, the most important questions we need to answer if you want to know whether our systems are secure or not. And I'll try to answer all those questions today. As a bonus, I'll try to prevent anyone from suffering in the process. So let's start with the first question. Let's see how we can deal with access to the system. If we give everyone direct access to manage everything, we have two options. Give everyone full admin permissions to everything, or give each person restricted access to specific resources. Now, if you choose the first option, we have to be religious because only praying to a deity of your choice will save us from potentially disastrous consequences. When I say disastrous consequences, I do not only mean someone with malicious intent will destroy everything, but also someone with good intentions will destroy everything by doing something random that should not be done. On the other hand, if you choose the second option, we have to be prepared for a lot, and I repeat, a lot of pain and suffering. If permissions are too restrictive, people will not be able to do their jobs. If permissions are too permissive, we will have to deal with people who have access to things they should not have access to. All that means that CLI tools executed by humans from their terminals are out of the question, at least when production systems are involved. CLI-based tools like Terraform or Pulumi require users to have permissions to manage everything directly. We either need to create an admin user with permissions to do everything anywhere, or create individual users, each with tailor-made permissions. The latter results in tremendous amount of work, a lot of suffering, and close to impossible maintenance. Those are the reasons why companies tend to set up a central server from which we can access everything and give everyone access to that server. But that does not solve the problem, except that we are in a better position to track who does what and what was done. That allows us to at least know what was done, but not necessarily to prevent intentional or unintentional destruction of everything. However, I already said that having a central server is not a solution either, even though many are really doing it, using it. There is a solution though. If we move the management of resources to Kubernetes, we can avoid giving direct access to specific resources like AWS, Azure, Google Cloud, and enable users to manage them as Kubernetes resources. That, however, still does not change the situation much. Those users still have to be able to manage everything, directly or indirectly. Still, it's already better than it was. There's no need for providing credentials to float around or for making people's lives miserable by saying so no one can do it. If you manage everything from inside a Kubernetes cluster, it becomes a control plane to manage everything, no matter whether that's workloads running in that cluster, workloads running in other Kubernetes clusters, or workloads, infrastructure, and services running somewhere else. Now, you might be thinking that Kubernetes is the solution only for running containers inside the cluster, but that's not true. Kubernetes is orchestrator of resources. What those resources are depends on controllers, and controllers can be anything. We have controllers that manage VMs inside the cluster, like KubeVirt. By the way, there's a video over there. We have controllers that manage applications as WASM modules, also inside that same cluster, but we also have controllers that manage resources outside of that cluster. We can use Cluster API, another video, to manage other Kubernetes clusters. We can use Crossplane, yet another video or videos, to manage everything, no matter whether the resources are in AWS or Azure or Google Cloud or somewhere else. All in all, Kubernetes is first and foremost an extensible API powered by controllers that can manage any type of resources. We can, and we should, use it as a control plane that acts as a single entry point to everything. As a result, it is the best candidate for RBAC control. Instead of trying to figure out what are all the places from which we can manage resources, we can just say that thing here or there is the control plane. Everything is managed from there. As a result, that control plane is the place where we need to define RBAC. Now, Kubernetes already gives us everything we need to do that. We can define who can create, read, update, and delete which resources. We can divide people into groups, and we can assign them to access specific namespaces and make sure that RBACs are enforced. So, a single Kubernetes cluster becomes a control plane where, among other things, we implement RBAC that defines who can do what. Moreover, RBAC does not have to be limited to humans. The control plane is the perfect candidate for implementing RBAC for machines. That's the place from where both humans and machines or processes can manage everything. But there is a problem though. Managing everything from a Kubernetes cluster means having hundreds or even thousands of custom resources or CRs. As a result, we need to define RBAC for all of those CRDs, definitions from which we get CRs. And that can be very, very, very painful. I dare you to go through each of the resource definitions or RDs or custom resource definitions or CRDs and define RBAC for each of them. Remember, it's not only about defining who can create and read and update and delete which resource, but which fields of those resources can be modified and what are the acceptable values for those fields. Now, the good news is that we can solve that problem too. We can do much better than defining RBAC for every single RD or CRD. The solution to the tremendous number of resources is to create CRDs and controllers yourself. So, instead of saying you have permissions to manage clusters, node groups, gateways, VPCs, subnets, and so on and so forth, we can say here's a CRD to manage a cluster. All you have to do is create a CR called, let's say, complete cluster, and the controller will make sure that the cluster and the node group and the gateways and VPCs and subnets and so on and so forth are managed. There is no good reason for you to have access to all of those. As a matter of fact, majority of people do not want to have access to all of those. For example, a developer probably has no interest in defining and managing a deployment, an ingress, a service, and horizontal pod autoscaler, and so on and so forth. It makes much more sense to define and manage, let's say, a custom resource called application, which in turn will create all and manage all of those. That can be meta controller, videos over there, crossplane compositions, another one over there, or any other similar tool. As a result of creating your own CRDs and controllers and offering them to the rest of the organization, wherever you work, to create so that people can create CRs, we can accomplish two goals, two of them. To begin with, everyone's experience with managing stuff, whatever that stuff is, will be easier. But more importantly for this subject, we will have much easier time defining RBAC. We can say, you, human, you can create and manage a custom resource called app or SQL or cluster, and the controller, the machine, will do the heavy lifting of expanding that into deployment, services, ingresses, node groups, gateways, VPCs, subnets, or whatever else is needed. We can restrict who can manage those custom resources by namespaces and say only those who can access and manage namespace X and Y can manage clusters through those controllers. If you can access that namespace, you can do it. Otherwise, bug off, go away. So that solves the issue of easy management of RBAC, but that's not enough either. Being able to define who or what can create, read, update, and delete which resources is not enough. We need to figure out what are the acceptable values for those resources. What is the correct spec? Now that we figured out how to effectively control who can do what, we need to figure out what are the acceptable values for those resources. That's where policies come into play. We can use them to define all acceptable values, thresholds, required fields, and so on and so forth. These days we can do that easily with tools like OPA Gatekeeper, Kyverno, Datry, or Kubernetes Validating Admission Policy. By the way, I covered all of those, which is baked. The last one is baked even in Kubernetes, or will be when it stops being alpha and when it goes GA. But at the time of this recording, that's not the case. So you might want to scratch the last one, Kubernetes Validating Admission Policy. Now, if you forget everything I said so far, we would need policies for almost every single resource that can be defined in a Kubernetes cluster. Deployment, service, ingress, horizontal port autoscaler, vertical port autoscaler, and so on and so forth. If we extended Kubernetes, as we should, we would need policies for all those custom resources as well. Argo CD project and application, Knative service, MongoDB operator, and so on and so forth. Now, if on top of all that we had resources used to manage external services and infrastructure, we would need policies for all of those as well. We can easily get to hundreds or thousands of resource types. Now, besides the sheer number of policies we would need to create to match all those resource types in Kubernetes, we have another problem with policies. Most of them, at least those you should be using, are based on admission controllers. And now you might be saying, wow, you were so positive towards admission controllers, and now you're going to say something bad. And yes, I'm going to say something bad about admission controllers. Now, if you're not familiar with admission controllers, you should watch that video over there, since, among other things, it explains how they work. So I'm not going to go deep into them, except to say that Kubernetes admission controllers are validating each resource individually. And that is a huge problem. If an application Kubernetes consists of a dozen of resources, deployment, ingress, service, horizontal port autoscaler, and so on and so forth, and each is validated individually, our policies will not work. Now you might be confused. Why? So let me explain. Here's an example. We cannot have a policy that says the application needs to be scaled if that scaling could be defined inside the deployment, or as a horizontal port autoscaler, or as SCADA. How do we know whether any of those is applied, or if the number of replicas is set in the deployment itself when we validate that deployment? The only reasonable way to apply policies based on admission controllers is to wrap all the required resources into a single resource that we can validate. That's why we should create our own CRDs and controllers and offer them to the rest of the organization and deny access to all others. Resources based on those CRDs would represent a real unit of something, like a backend application, a database, a cluster, and so on and so forth. With those, we can easily define both RBAC and policies. And on top of that, and apart from the benefits we already talked about, That will also make it easier for everyone to manage their resources. There is no such thing as an application or a database in Kubernetes. All we have are building blocks that we can wrap into something meaningful. Now let's spice it up a bit more and remove access to the control plane cluster to all humans. Heck, let's go even further and deny access to the control plane to everyone and everything, to both humans and machines. Let's allow only machines to access it, but in a very, very specific way. Now I'm going to say something contradictory to what I said earlier. You do not need RBAC, except in break glass scenarios. What? You heard me right. You do not need RBAC if you use GitOps, or to be more precise, you do not need it in the same format as we discussed earlier. So, let me explain. Typically, we push information to Kubernetes API. We can do that by executing commands like kubectl apply or helm install and so on and so forth. We can do that ourselves or through processes like CI/CD pipelines. It is a push-based model. GitOps turns that around. Instead of pushing information to Kubernetes API, tools like Argo CD over there and Flux over there and Carvel Cup Controller and Rancher Fleet, that's there as well, are running in the cluster, pulling manifests from Git repositories and applying them to the cluster and performing continuous drift detection and reconciliation. As a result, we do not need to be able to access the cluster directly, but use Git as the proxy. We push to Git what we want to have, the desired state, and we let GitOps tools ensure that the actual state in the cluster is the same as the desired state. Bear in mind that GitOps tools do not ensure that the actual resources are in sync with the desired state. GitOps is ensuring that Kubernetes resources are in sync with what is defined in Git. And from there on, Kubernetes takes care of ensuring that the actual state is in sync with its own desired state. It's Kubernetes that converts deployments into replica sets, which create pods, which ultimately run containers. In case of a deployment defined in Git, the actual state is containers wrapped into pods. If you define KubeVirt machines, Kubernetes converts those into real virtual machines. Similarly, if you define crossplane manifests, Kubernetes converts those into cloud or other types of resources running outside of the cluster itself. Now, let's get back to RBAC and policies. Do we still need those if you use GitOps? Well, yes, we do need RBAC, but for different reasons and maybe in different places. To begin with, we might have a break glass situation that might force us to temporarily stop GitOps synchronization and intervene manually. To do that, we need to enable access to privileged users. That, in turn, will result in a limited number of RBAC roles, probably with full admin permissions. On top of that, we will need to assign permissions to GitOps tools so that they can perform the operations we need them to perform. Assuming that we are aligned with using CRDs, that means that those tools should have read-write access to all CRDs we think people should be able to manage by pushing manifests to Git, as well as read-only permissions to all other resources so that GitOps tools can track their states. In other words, we are translating permissions we previously gave to humans into permissions used by specific tools running in the cluster. On the other hand, we are controlling human access through Git, not by giving people access to enter that control plane cluster or anything else. Who can create a pull request and who can merge it to the main line of a specific repository? That is the real question. Git becomes the interface between humans and the control plane cluster, which in turn is managing everything, no matter whether that something is in the same cluster, in some other cluster, in the cloud, or anywhere else. How about policies? Well, policies stay the same, except that it is not kubectl, Helm, or other similar CLIs and tools that are sending manifests to the Kube API, but it is now GitOps that is pulling manifests and applying them to Kube API. In any case, requests are validated with admission controllers independently of who or what tried to apply them. Now that we know who can do what through RBAC, that we know that resources will be defined correctly and with good practices in mind, which is through policies, and that we are pooling information from Git through GitOps, we can turn our attention to containers. How do we secure them? Well, there are three answers to that question: SBOM, signatures, and image scanners. We want to know what is running in a container, and that's what SBOM gives us. It allows us to collect a software bill of materials, or SBOM, as full list of everything in a container image and beyond the image. We want to ensure that the container image we are running is indeed the one we built and not something else or something that was tampered with. That's where signatures come in. Dive in. We can sign an image right after we build it, and we can validate that the one we are using is indeed the one we signed. We can do that validation inside the registry of choice, if it supports that, or we can do it in one of the policies with, let's say, Kyverno. I have the video about that as well. Finally, we want to ensure that the container image we are running is not vulnerable to any known vulnerabilities. That's where image scanners come in. Typically, we would run scanners either as part of pipelines that, among other things, are building and pushing container images, or inside container registries themselves. Harbor, for example, allows us to scan images as they're pushed there, and we can choose one of the few supported scanners. Watch that video as well. But wait for it, we are not done yet. There's still one more important thing we need to do. We need to prevent our cluster from becoming a target for WikiLeaks. Some of the workloads will need access to confidential information. That's how it is. That can be authentication to a database, a password to a service, or one of many other things that shouldn't be exposed to the outside world, and sometimes not even internally. How do we deal with that? More often than not, confidential information would be available as Kubernetes secrets, which in turn might be mounted to containers and available as files or as environment variables. In some other cases, even Kubernetes secrets are not allowed, but I will skip that scenario for now. So we know what is the end state, Kubernetes secrets, but how do we get there? A Kubernetes secret is created like any other type of Kubernetes resources. We can create them by executing kubectl create secret from someone's laptop, but that would result in someone having to memorize the secret in case the cluster goes down and needs to be recreated. We can define a secret as a YAML manifest, but we cannot push it to Git for obvious reasons, right? We need to have a better way to deal with secrets. And we do. There are many ways to work with secrets in a safe way, but today I'll focus on two. The most common way is to use a secrets management tool like HashiCorp Vault or secrets managers available in your favorite cloud providers. All of the hyperscalers like Google Cloud, AWS, and Azure have their own secrets managers. That's fine. That's great. Secret managers are designed to store secrets, but how do we get them into the cluster? How do we get from the secrets stored somewhere to the applications that need them? Well, that part is easy. We can use one of quite a few tools that synchronize data stored in secret managers with Kubernetes secrets. We can use external secrets operator, watch it, by instructing it which data from a secret store should be synchronized into a Kubernetes secret. We can accomplish a similar result with secret store CSI driver, video about that, but with data synced into Kubernetes volumes instead of Kubernetes secrets. Or we can go with Vault operator, or we can, you get the point, right? We have the tools to do that, but we can also take a completely different direction. Instead of keeping data in a secret store and then syncing it to Kubernetes, we can use something like sealed secrets. There's a video of that as well, to skip secret managers altogether and encrypt secrets inside a Kubernetes cluster, the cluster itself. That provides a huge benefit to those practicing GitOps, since those secrets can be stored in Git. Since they can be decrypted only by the cluster that encrypted those secrets, the manifests with encrypted secrets are relatively safe to store in Git. Once manifests with encrypted secrets reach the cluster, sealed secrets controller decrypts them and creates Kubernetes secrets. Git, in a way, becomes the secret store. We did not explore everything that could be done to make Kubernetes clusters secure. We did not touch TLS, confidential computing, and quite a few other things. Nevertheless, by following the presented guidelines, we should be able to build a secure cluster that is safe to run production workloads in without the expense of making everyone suffer in the process. Remember, security is important, but not at the cost of productivity. We should be both safe and productive at the same time. We should be able to continue to move fast and break things. So I try to focus on both, even though security is the main objective, today at least. We went through RBAC, but we simplified it with the usage of custom resource definitions, or CRDs. We implemented policies, but we simplified them as well with CRDs. We implemented GitOps, which helped us remove the need for direct access to cluster. We learned that signing images and scanning them is a must, and we figured out how to propagate secrets from secret stores, including Git, to Kubernetes secrets. That's it, folks. Stay safe and secure.